All right, so first I want to start by adding something that I forgot in the last video about the de Broglie wavelengths. And we talked about matter being waves, that it wasn't just like electrons weren't just particles, but they were also waves. And I forgot to mention any of the actual experimental evidence for this. And it turns out uh, that electrons will produce interference patterns if you put them through similar situations like the double slit experiment for light. You can actually do that experiment again with electrons, and there will be an interference pattern produced by the electrons. If you want, look in your book for a little more details on some of these experiments, but I just wanted to make sure you did know that there is experimental evidence that supports the idea that matter is both a particle and a wave. So in this video, we're going to go over what is the uncertainty principle. Okay, and so what this is an idea in quantum physics that there are certain things, certain measurements that you would want to make, and there are certain ones that just they don't go together well. If you measure one, it messes up your measurement of the other, kind of thing. And originally, this was thought of as something that was just a limitation in our ability to measure these situations, which is kind of how it gets explained to you conceptually. Although it didn't take long for the opinion to change to this being something more built into the universe. There is kind of some little experimental evidence that kind of seems to suggest that this is actually just something that is uncertain just in the universe, and it's almost like choices that particles make when you go to measure them. That they kind of have this fuzzied out little bit of data for this. Speaking of this conceptually, we're just going to go ahead and write these down. The two that you're worried about knowing is the relationship between some of these pairs of things you can measure is momentum and position. These two, basically you can't know both of these at the same time. And so what happens is you'll have an uncertainty in position times the uncertainty in the momentum, and it has to be greater or equal to h over 4 pi. And then another one that you're expected to know about is energy and then the time that it had that energy. So energy and the time for that energy, sort of the time when it had that energy. And that's similar form delta E, delta T has to be greater than or equal to the same thing, h over 4 pi. So this one, energy and time, explaining this one conceptually is a little difficult, but this one we can at least kind of think about if we start thinking in terms of waves. Now, if you remember, the momentum of a wave, like for light, is based on its frequency. So I could draw a wave that is very clearly defined as far as its frequency goes, right? So it has, something like that. And I have a pretty nicely repeating frequency that you could look at, and you could measure this thing's frequency, and you'd know its momentum really well, right? But if I asked you to tell me where, I'm going to go over it in red just so it's a little more visible, where is this wave located? If this is a particle, the particle in quotes, if this is an electron or something, this is the wave function for an electron, where is it located? You can't really tell me that. I mean, is it mostly here in the middle? Is it a little off in the middle? Is it kind of over here? Where is it going to be? So when we have this nice wave like this, and especially if you're thinking in terms of a probability wave, we can't really tell you where it is at any moment while the wave is in this form. If the wave, though, looks like this, so right here, sorry, this, when it's in this form, momentum, we know it really well. Position, no, not so much. We can't really measure it very well. It's somewhere in this area here-ish, but we can't really narrow it down. Now, what if the wave function looked more like this? Well, if we look at that, it has a pretty clearly defined location. It's in here. It's in this bump. It's not in any of these other bumps or anything like that. But what if I asked you, so here, position, we've got. But what if I asked you to tell me the momentum of this? Well, you'd have to look at the frequency of this wave, and what is the frequency of this wave? It's just a single pulse. So if we get the position known really well, then the momentum becomes something we can't really measure. So in a situation like this, we can measure the momentum really well, but it hurts our position measurements. In a situation like this, we can measure the position really well, but it really kills our momentum measurement. And so, conceptually speaking, that is the idea behind this uncertainty principle. The more well you know the position, the less well you know the momentum, and then the more well-defined you do of the momentum, the less well-defined you do of the position. And then the same thing over here for energy and the time at which it had that energy. We may be able to say really precisely this is exactly what energy we had, but then we wouldn't be able to tell when we had it. And if we try to measure the time at which it was happened, then we're not going to be sure exactly what energy it had at that time. There are some good examples for using this in your book. The basic idea is, you kind of have to do some estimates on these with these versions, since these are kind of a little bit of watered down versions from their real versions. And so, like, if you were trying to figure out if a particle could exist inside of something, I think an example in the book is if a particle can be inside the nucleus, and you would treat the radius of the nucleus as delta x, and then you would try and go in and calculate what momentum would that require for it to be confined, and it must be inside this certain area. You solve what momentum would be required of this, and it turns out the momentum is, well, I don't want to ruin it for you. I don't want to tell you. Read the example in the book. It's a good one. And the same thing for energy and time, kind of stuff. You might look at a situation and say, well, you look at a time and it's kind of like, what would the average time be, or what would if this was something changing energy orbitals, then you might use the energy that's halfway between the two of them for the energy, and then you figure out how long can it exist there before it decays down, kind of thing. So there are a few little tricks. Give a little examples there. It would help you a lot to go look at those. Another way to think of this uncertainty principle is to imagine that if I had a particle, if you want to think of it not in terms of these particles, but let's say I had a particle here and I wanted to measure its position really well. Well, then I would send in a really high frequency photon at it, and the really high frequency would bounce back, and all the extra little wave crests and everything would give me very fine measurements of this thing's position. But this would be a very high energy photon. So when it collides with the particle I'm trying to look at, it's going to really affect its momentum. So it may be able to tell me its position really well, but it's going to change its momentum by a great deal, which would then make me have a poor understanding of the particle's momentum. And if you change to the opposite, if you do a really long wavelength that you send in of radiation to measure this thing's position, well, now you're losing out on details, right? It's like you went from here, you were measuring with a meter stick that went all the way down to millimeters, and now you're measuring with a meter stick that only does to like, that has no markings on it at all, and it can only tell us within a meter. Well, we lose out with this big long wave the details of the position of the particle, but this lower energy wave has less of an effect on its momentum, and so we can figure out what its momentum is very accurately. Mathematically speaking, when you get into quantum mechanics, like I talked about before, I said there was a reason I wanted to talk about it, is that you had that psi. Remember this wave function psi, and I told you to think of it as some abstract vector pointing out in space. And if you wanted to know what the position of something was, you had to project this into the position basis. You literally had to take this and you say, oh, down here is our position basis, where here's x1, here's x2, here's x3, and there's literally an infinite number of these abstract kind of positions. Here could be x4 or whatever, all these different x things. You would project this vector onto that space, right? And it would project out like this, and then you'd look at what was its component in each of these directions, how much of it was in those directions, and it would tell you that probability. So you could get a pretty good measurement of this position. But while it's projected into this position basis, it is then not projected into the momentum basis, right? And then at that point, you lose information about the momentum, and vice versa. If I project this into a momentum basis, right? So same sort of thing, same psi, but this time I'm projecting it into a momentum basis where we have these momentum P1s and P2s, and this is not visually how it really be because it's infinite dimensional. I can't draw it. P3, and then I would project this down into the momentum basis somehow, and then I would look and say, all right, now I've cast the shadow of this down onto this momentum basis. What's the length of it over here and here and here? And I'd find all these lengths of these components again, but at the point of doing that, now it's not projected into the position basis anymore. And so I lose information about the position. And any two vectors that any two measurements, if you want to make a measurement about position, you have a position operator. And what this operator does is it does that projection for you. It projects psi into the position basis. And then you have a momentum operator, and it projects psi into the momentum basis. And if it into this momentum space. And it turns out that this uncertainty principle will hold for any two operators, right? Because that's what these things do. It isn't the momentum and the position. It's an operator that pushes this and projects it into the position space, and it allows you to then make measurements of the position or calculate them, or an operator that pushes this into the position or the momentum space and allows you to make then predictions about the momentum. Well, it turns out if any of these two operators, like the position operator and the momentum operator, if they don't commute, in other words, if this is not zero, then the uncertainty principle will apply to them. And what I mean by this is something called the commutator. This isn't something you need to know again at this level, but just this is called the commutator. You're not going to see this on your test or anything. And basically what it's telling you to do is do delta x delta p operator minus delta p delta x. And if you look at most things like multiplication, 3 times 5 minus 5 times 3, it'll equal 0. Well, if the order actually matters for these operators, if you do them in the reverse order and it doesn't give you the exact same thing and it doesn't equal 0, then it is said that these two things don't commute, and then there will be an uncertainty principle for them. It means you can't know them both at the same time. You can think about this in any of the ways that I just talked about, any of the ways you want. Here is the wave way, here as the high frequency wave versus the just single single crest wave, the measurement limitation, or even just if this mathematical kind of abstract way here makes a little more sense to you, of projecting it into one basis means you can't then have it also projected into this other basis as well, and they don't commute, this kind of abstract mathematical thinking, then that's fine. But this abstract mathematical thinking, this is not something, this one right here, of any of them, this is the one you don't have to know. You're not going to be asked this, and quite frankly, if you tried to explain it probably on your exam at the end of the course when they're grading it, I'm not sure they're going to be happy with you going through and talking about the commutation of them, especially since you don't really know what these operators are just yet at this level. It involves calculus and all kinds of stuff, derivatives and things like that. So I just wanted to give you this idea, if it even helps you or not. If you don't understand this whole projection idea, don't be upset. Just ignore anything I said about it in the last video or this video. Okay? The next thing we have to do with this is you can go through and you can look in your book again for this calculation. I'm not going to go through and write this whole thing out. But we need to talk about the ground state of hydrogen. And this is actually a very, of the hydrogen atom. This is actually very useful because if you take other atoms that are larger than this, they are called hydrogen-like atoms. Knowing this allows you to do just small corrections to figure out what they are. So like a hydrogen-like atom would be something like iron, an ionized iron atom where there was only one electron left. Because if you think about hydrogen, it's basically just a proton, and one electron bound together. And if that's the case, you'll find that the energy of that electron-proton system is this. It turns out to be this, negative 13.6 over n squared. So what orbital is that electron in? Is it in the first orbital, the second, n equals 1 equals 2 equals 3? Which orbital is it out in? Electron volts. So obviously for the ground state, n would be equal to 1, and this would just become the energy in the ground state would just be negative 13.6 electron volts, which we have seen before when we were looking at these energy levels in the hydrogen atoms, talking about them being with these negative potentials and all that kind of stuff in previous topics. So that's just a little way you can look in your book and see that little derivation of it, but you do have to know how to use this. You don't have to know how to derive it, and I feel like I've already gotten too complicated with all this stuff, so I'm not going to go through that. Just know it, know how to use it. Whatever orbital it's in, you need to put in for n. Whatever energy state it's in, you put in for n and calculate away. The last thing I have to go over for this 12.1 topic for this whole first thing is tunneling. Okay, and this is tunneling, and I have a couple ways to go over this. The first way is the idea that there's that quantum uncertainty in the energy associated with things, so that these particles and stuff, they can basically borrow energy from its surrounding. And so let's say we had some sort of barrier here, like a wall for a particle, and this particle with the energy that it has couldn't make it through. It's kind of like I have a little ping pong ball and I'm throwing it up against the wooden door. The ping pong ball is not going to be making it through the door. Well, quantum uncertainty allows for there to be a slight uncertainty in the actual energy of that thing, and it can essentially borrow energy from its surroundings for a moment, get a little wiggle room in its energy, have enough energy to actually make it through the barrier, and then give that energy back so that it's all conserved. And so what you'd have is something that looked like this for the wave function for it, where the wave function would look something like this, and then inside the material it would drop off, and then outside you have a much smaller wave function. Now, when you're looking at this, when you look at this wave function here, not psi squared, but the actual wave function, so that comes down below it. Before you square it, you would then square this, right? If we squared it, it would look, something more like, this, where it's up taller. Sorry, that should have been as tall. Where you'd have this as your probability for where to find it, and then you have a little probability in here, and then over here you have this smaller probabilities. And so if you were looking for this particle, you would say, all right, I'm very likely to find it on this side, and then these crests over here are smaller, so you're not as likely to find it on this side. But if I shoot a million particles at this, I am going to find some of them that actually are on this opposite side of the barrier and not over here on the side. Even though they didn't have enough energy to make it through this barrier, I will find some that have passed through this barrier. It's pretty unlikely, but essentially that is the case. Anywhere this probability wave extends, you look at how tall it is, you have the chance of finding it there. This is the idea of tunneling. It's even used in some medical instruments to make them work. You shoot a bunch of particles at a barrier, and there's a certain percentage that should make it through. Now, this lower wave over here on this side doesn't mean that a particle on this side has less energy than one that didn't make it through. In fact, the energy over here would be the same as it was before. It would have gone through this as though it wasn't there, almost ghosted or teleported its way through. This lower amplitude doesn't mean lower energy if you find a particle on this side. It's not losing energy as it goes through this barrier. It's just less likely to do it. And this sort of thing, I believe, even applies to orbitals. When an electron changes from the n equals 1 to n equals 2 orbital, it doesn't actually travel in the space between, because remember, it can't exist in the space between. It actually tunnels from one orbital to the next. Another way to think of this, and I drew these pictures in the last video, but going back to this particle in a well kind of thing, we have the one probability wave that looked like this. If you remember, it looked like that. And so if you went and looked for the particle, this was the n equals 2 state, the n equals 2 whatever in the one-dimensional version of this particle trapped, you're very likely to find it in here and here. But right in the middle, you have no chance of finding the particle there. So if we took and put a barrier right down the middle, right, and an infinitely, impossible to pass through barrier right in the middle, these particles that we created in this situation, they wouldn't notice, okay? Because the particle would be able to essentially tunnel through this barrier because it never can actually exist in the middle, so it never has an opportunity to even interact with this barrier or even know it's there. And so this would be another form of tunneling. If this was a, if this little box that we have this trapped in wasn't infinite on both sides, then even this little wave right here doesn't go down and it doesn't become zero at the edges. It actually will trail out and approach zero without ever actually touching zero. It'll asymptote to zero. Now, what that also means is that not only if you go to look for the particle in this box, that there's a chance that not only is there a chance of you finding it inside the box, you're very likely to, but there's a chance that you go to look and you don't find the particle inside the box, you find it outside. This would be like I put a basketball in a hole in the ground, and the basketball didn't have enough energy. It was bouncing, but it didn't have enough energy to bounce as high as the boundary of the wall, but yet still somehow I went and looked, and the basketball wasn't in the hole anymore. It was outside the hole. It doesn't have enough energy to get out, but there is a small probability that it could get out. And in fact, there's a small probability this can go, and you go to look for this particle that you put here, and you find it on the other side of the galaxy or the other side of the universe. That is possible. It's just extremely unlikely. So there is the idea. I believe they make a joke about this in the Hitchhiker's Guide to the Galaxy. They have the improbability drive, and the idea is what it does is it takes things that are very unlikely to happen, and it makes them very likely to happen. And so my understanding of what they're making a joke about is if you're in your spaceship, right? You have your crazy spaceship. You're flying through space. And what it does, this improbability drive, is instead of pushing you with fire or flames or some sort of warp drive, what it does is it says, all right, there is a possibility. This is where you are over here, and you're at position A, in this over here on this side of the galaxy. Well, there is a slight possibility that one of the particles of your plane, like I go to look at one of the little particles, the electron, that I don't find it here, but I find it over here at way, way far away on the other side of the galaxy where you want to go, at position B. So this particle was actually way over here when I went to measure it. Well, the improbability drive takes it a step further. What it's basically doing, at least my understanding of what they're talking about in that, I hope this is the way they meant the joke, is that what it does is it takes not only does it make this unlikelihood of this one particle being over here, but it makes it even crazier, more unlikely that all of the particles, when you go to measure them, happen to be over here and over here in the exact same order relative to each other as they were back over at position A. So the way this drive works is it takes advantage of this tunneling effect, and it makes it extremely likely that every particle in your whole ship will tunnel to the exact same location in the same configuration over right where you were wanting to be at that moment. Okay? And so it's kind of a little joke in there. I don't know how you would ever make that drive a real possibility, and it doesn't work very well. If you read the book or watch the movies, it doesn't work very well. They always end up with all this crazy stuff happening with whales popping into existence and stuff like that. But that is the basic idea, that you can look for something and it would be there. Now, don't sit here and stare at your computer and expect that at some point it might tunnel to the other side of the room, the whole computer together as one piece, or suddenly disappear because all the particles tunneled to different places all over the galaxy. The odds of that happening are extremely low, and the odds of even just a single particle tunneling to the other side of the universe or even to the other side of the room is very low, let alone all of them at once. So you have an extremely, that definition of what forever is. I'm sure if you calculated it out, you would be waiting there many trillions and trillions and trillions of times the age of the universe, or it's just not going to happen. But the basic idea is on small scale individual particles, it can actually have a pretty high likelihood and is something you are going to have to deal with on the small molecular scale. And anything on this large scale, like in Hitchhiker's Guide, is more like something we think of just for fun. Okay, that's pretty much it for this, and that finishes off this topic.